Hello everyone, today we're going to be covering ASM bytecode manipulation in Minecraft modding. The contents of this talk, I'll be covering what bytecode manipulation is, its uses in Minecraft modding, for example when to use it or not to use it, an explanation of how bytecode works, how it's generated, and then I'll get into the Minecraft specifics such as creating a core mod and then creating a class transformer. Yes, what is ASM bytecode manipulation? Well, every Java program you make gets turned into a set of instructions which is interpreted in the JVM, or otherwise known as the Java Virtual Machine. This set of instructions is also known as Java bytecode. Object Web ASM provides a way which you can modify the Java bytecode before it is executed. This is why it's called ASM bytecode manipulation. Modifications can be adding, changing, or removing these instructions. Uses in Minecraft modding. This allows you to change the code run by other classes by modifying that class's code at the bytecode level. This is also known as a class transformer, and Forge adds the ability to create this with ASM. Not only can you use class transformers to edit vanilla Minecraft code, but you can transform classes from other mods and your own if you desire. To make a class transformer in Forge, you'll need to make what is known as a core mod. So when should you use ASM bytecode manipulation in Minecraft modding? Well, to be honest, it should be used sparingly, and should be used if there are no other options. Alternatives can be, for example, if you need to access a field that is non-public, then you should use an access transformer or reflection. There are many tutorials out there on this, so have a Google and you'll find a lot of them. If you need to replace an item or a block completely, then you need to create a custom blocker item of your own and then change all the references in the Minecraft code in a way or another from the old one to the new one or override it in the registries. So completely replacing an item or a block class with ASM causes compatibility issues with other mods trying to use that class. So let's say that you wanted to make a new chest. You'd remove all the recipes to the old chest and create a new recipe from which is similar to the old one but points to your new chest. If you want an additional event hook, then you could submit a Forge PR to get it added. However, if it is highly specific, it is better to use a class transformer. If you want to stop something in vanilla occurring, try cancelling the event with an event handler and recreating the following steps with your modifications. However, if the event is quite significant and performs many actions, such as player interact event, then it may make sense to use a class transformer instead. Some legitimate uses are adding highly specific event hooks that are only useful for this mod, and modifying an aspect of a class that there is no other way to manipulate. The pros are that it gives you the ability to transform any class, whether from vanilla or another mod, and ASM comes packaged with Forge ready to use and adds a way to register your class transformer, so it takes away a little bit of the hassle. If another mod also uses ASM on the same class, then they can conflict. And it also can stop working in a Forge update if the class you are transforming changes. So let's say that, one of the days the Forge adds an update and it completely changes the class, or it even adds a single line, then your ASM bytecode manipulation could just stop working there and you need to recreate it. It can be difficult to debug if errors arise, and it's also time consuming to do this. So how does bytecode work? Bytecode is a set of instructions, and it interacts with a stack and a local variable table. The stack can be thought of as a list of operands. If Java were to perform 1 plus 1, it would push 1 to the stack, then push 1 onto the stack again, and then it would perform an addition operation, leaving 2 onto the stack. If this operand is no longer needed, it can be popped off the stack, and the stack will hold these operands similar to an array list, and operations carried on the stack will operate on the topmost operands of it. So first thing you should notice is that in the stack, it's not necessarily ordered like 0, 1, 2, 3, 4. You're never going to address a stack by the index in it. You're never going to say, get me the fourth variable in the stack. You're always interacting with the top value in the stack. So if I pushed 1, then it would push 1 onto the stack. If I pushed another 1 onto the stack, it would push that 1 onto the top, and it would push the other 1, which was there, to the bottom. Then, if we performed an add operation, we would add them and leave a 2 on the stack, popping off the other 2. If we pushed a 2 onto the stack, then it would push the other 2 that we had before down and push a new 2 on the top. If we push a 1, it'll push a 1 on the top and then put the other 2's down 1. If we add, it will add the top 2 values only because the add is only affects 2 operands, and it will leave a 3 there. If we pop, it'll take the 3 off the stack. If I push another 3, then it will push the 3 on the top and put the 2 down. There's also a swap operation which will swap the 2 and the 3, and pop which will pop off the top value. So yes, you can save variables with bytecode because, as you can see, the stack works off having things temporarily going on there and popping off as you need it. So we save these variables in a local variable table. The local variable table stores values and is referenced by its index, similar to an array. If I wish to save a value, I would ask it to store it in index n, but I'd need to have the value that I'm storing on the top of the stack. If I want to retrieve it from the local variable table and put it onto the stack, then I would ask to load it from index n from the local variable table. A stack, a local variable table, and a reference to the runtime constant pool together is known as a frame. You should not need to worry about runtime constant pool when manipulating bytecode, as the Java compiler and the ASM will deal with it for you. A frame is created each time a method is called. Let's say we've got here a frame here. I haven't put the runtime constant pool in it for simplification, but we've got the local variable table here. As you can see, we do address local variable table by index, so I've got it as position 0, 1, and 2 to show you how it works, and the stack's still at 1, 2, 3 because we don't ever address it by its index. So I'd push hello onto the stack, and I'd store it in position 0. Now notice how that it takes it out of the stack when I store it in there. If I push a test to the stack, I'll store it in position 1 on the local variable table. I'll push world onto the stack and store it in position 2 on the local variable table. Now I'm going to load 0. So what this does is it'll load the value from the local variable table in position 0. Also note that it doesn't remove it from the local variable table. The local variable table stays the same every single time. So if you load or store things from it, it doesn't remove it. Then I'll load 2. So it won't load test, it'll actually load world instead. So I'm just showing here how the indexes work. So I can load 0, then I can load 2, and I'll get the 2 strings hello and world. And then I can perform concatenate, which will concatenate hello and world. So now I'm going to cover how to invoke a method using bytecode. To invoke a method, you must first have the parameters on the stack and then invoke the method. So if you are calling a non-static method, you must also push the instance you're invoking the method on before the parameters. So if we were performing a non-static method that is on an instance, then we'd push the instance that we're invoking it on first, then we'd push the parameters that we're going to be using, and then we'd invoke the method. After calling the method, the parameters and the instance are popped off the stack and are either replaced with nothing or replaced with what is returned. I should also notice that the order that you push the parameters in is important. So you should always push the first parameter first and the second parameter second. This will mean that on the stack you'll have the last parameter on the top and the first parameter on the bottom. So it may look a little bit confusing, but that is how it works. Here's an example of the stack and invoking the method. I've left out the local variable table. However, if we did have it here, it would store the a.b and the dot to the local variable table. So, it would only store the a.b to the local variable table. So firstly, we'd push a.b to the stack. Now, if we had the local variable table, it would store that a.b there, and then we'd need to load it again. Now we're going to push the dot to the stack. So these are both strings, keep in mind. And then we're going to invoke string.split. So what we've done here is we've taken the a.b, which is the instance that we're invoking on. This a.b is technically the a in our code. However, we're actually going to be using the a.b as the reference to it. And then dot is the parameter that we're passing to it. And performing string.split will perform pretty much a.b or a, the reference to that, dot split, and use the dot as the parameter, leaving us with this simple array of a and b. So how is bytecode generated? Well, bytecode is what is generated by the Java compiler and interpreted by the JVM. The bytecode is a set of instructions, and each instruction comprises of an opcode, which is 1 byte, along with 0 or more bytes for passing parameters. An opcode is the type of instruction being carried out. Given that an opcode is 1 byte value, there is space for 256 types of opcodes. However, only 198 of these values are currently used. So that means that in bytecode you'll have 198 different types of instructions that you can perform. An example of a parameter that can be passed is an index to a local variable table, or a constant from the constant pool. So each of the instructions will generally have a prefix if they are required. So if I was to perform the bytecode instruction iadd, it would add 2 integers. If I had ladd, it would add 2 longs. So if you ever see a bytecode instruction that has a prefix before it, you can refer to this table and understand what it is. I should also point out that when dealing with bytecode, booleans are represented as integers. The long and double takes up 2 slots. So what I mean is in the stack and in the local variable table, a long value will take up 2 positions in it. So if you had stored a long in position 4, then it will take up 2 of those positions instead of just taking up 4. And similarly, you've also got a reference, which is A, and that'll just store a reference to a class or a field or whatever the value is. So now we've got our some example opcodes. So you can see here that each of these have got a prefix on them because they're dealing with types. So in the first one, we've got aconst underscore null, which will load a null value onto the stack. Iconst underscore 0 will load an integer of 0 onto the stack. And you can see the rest, the iconst underscore 1 and fconst underscore 0 will also load that onto the stack. There isn't an iconst underscore, n for every number. It currently it only goes up to 5 for now because they're used frequently. But for other values, you'll need to load a constant from the constant pool. So if I had, say, a number that was 43, for example, then Java would save that in the constant pool, and I'd load a constant from the constant pool at the index n, and the constant pool will have that value, the number that we're storing, in the index at that position, and we load it from there. iLoad will load an integer from the local variable table at the index specified, and iStore will store an integer onto the local variable table at the index specified. ALoad will store a reference onto the stack, so it'll load a reference from the stack from the local variable table, and dstore underscore 0 will store a double into the local variable table. Here are some things that deal with stack management and mathematical operations. So you can see pop here will discard the top value from the stack. Pop2 discards the top 2 values from the stack. Dup will duplicate the top value on the stack. Swap will swap the top two values. And you've got iadd, irem, iand. So the first one performs an addition operation on 2 integers. Second one performs an integer operation of the modulo or percent, as you can see. And iand will perform a bitwise AND operation on the top 2 integers on the stack. And then you've also can convert between different types. So I2L will convert between an integer and a long, and D2F will convert between a double and a float. So now we're going to cover the opcodes, which are the conditional ones. So for example, if statements, for loops, while loops, they will use these. So the conditional statements are based off go-to statements of sorts. So we'll say if this value happens, then we'll branch off to this section of the bytecode. And those sections are based off labels, which we'll cover a bit later. But so let's say we've got an if eq bytecode, then it'll check the top value in the stack. If that value is 0, then we'll go to the branch. So the branch is the part of the bytecode which we're going to branch off to. And if it's not a 0 at the top, then we'll continue on. If any, we'll check if the top value is 1. If it is 1, then we'll go to the other branch, or we'll continue. If LT, we'll check if the value in position 1 is less than the position value 2. If GE will check if the value in position 1 is greater than or equal to the value in position 2. I should also point out that in each of these, if it's comparing a value, then it will remove those values from the stack. So now we've got some more complicated ones. We've got if underscore ICMP that's pretty much shorthand for if the integer compare equals. So in that one you can see if the two integers, when we compare them, are equal, then go to the branch, and if underscore ACMPNE will check if two references, when compared, are not equal. So if reference 1 is not equal to the reference 2, then go to the branch. Go to branch is another bytecode, and that will just simply go to that branch. iReturn will return an integer from a method, so this isn't conditional. This is when you've got a method and you need to return a value, you'll call a return, and generally if it's one of those simple types, you'll have a prefix before it, such as iReturn or fReturn will return that type, and return itself will just return a void value. We've also got a getStatic, which will get a static field value from a field reference in the constant pool index. So along with strings and integers and that, you'll also have the locations of the packages and classes for the fields and methods you're invoking. So for example, if I wanted to invoke a field from another class, that location of that field and the name of that field will be stored in the local constant, so not the local constant, the constant pool. And if we want to get the static value of that static field, then we will reference the constant pool at that index and get that value. Similarly, if we want to set that field value, we would get the value from the constant pool at that index and then set that value. Invoke virtual is how we invoke a virtual method. So you'll pretty much be using invoke virtual for every method that's not static. Invoke virtual will it comes with a parameter for the index, and that index comes with the package and class for which the method you're invoking is in, and the name of the method. Invoke special is similar to invoke virtual. It's only used for constructor classes pretty much, and for a few other cases, but whenever you see a constructor class that calls a super class constructor, you'll see the invoke special, and it will invoke super. And of course, the superclass constructor package and method will be stored in the constant pool of the index passed by the parameter. Invoke static, similar to the others, will just call a method that is a static that's in the constant pool index. New will create a new object, and that type is referenced in the constant pool. And similarly, instance of is another bytecode instruction which will determine if an object is of a type referenced in the constant pool by the index you've given it. So yes, I've covered some of the bytecodes, but that's not nearly all of them. That's just to give you a grasp of the different types you'll see. So now I'm going to show you Hello World in Java in your Java file, and then Hello World, what comes out in bytecode. So on the left side, we've got the Java file. It's a simple command line one, which will, given the arguments, it won't use the arguments, but it's still got it as one of the parameters, and will print the line Hello World. If you wish to view any class in its bytecode form, like on the right, then you'll have to have compiled it first, and then you can run a java p-c hello world.class in the command line, and it will show you the bytecode for it. There are also some IDE plugins which you can use to view the ASM, and which we'll be using in the tutorial section later. And so I'll show you how to install those later as well. But yes, on the right you'll see the bytecode, and this shows you the different types of instructions and the references to. So you'll see, like on the left, you'll have the bytecode instruction, and right there'll be occasionally a parameter to it. So here's a walkthrough of the bytecode itself. So you'll see all the entire bytecode. I've copied it from the command line there for you to see. This one thing you should notice is that this is a frame we're pretty much looking at. We're looking at the frame for the constructor method of the Hello World class. It comes with a constant pool. the local variable table and the stack. Um, the local variable table and stack will be different for every single method. However, the constant pool will be shared between the entire class because it's a reference to that constant pool. So in the constant pool, we've got 4 values which we'll be using, and you can see that in the code we've got a number 1, number 2, number 3, number 4, which is those values. In the local variable table, we've got this. That is because in the constructor we will be loading this. So therefore it's loaded in position 0. Generally, if you use this in your method, then it'll load it as position 0 in your local variable table automatically. ASM will tell you if it's loaded there or not, so don't get too hung up on deciding whether or not it's there. You'll see it later. It's very easy to determine what your local variable table is before it starts. Generally, this and the parameters of a method are loaded in the local variable table before it started, and anything you introduce, such as variables you introduce, are loaded in later. So in this example, we also don't have anything in the stack yet, which we're going to load now. First thing off, in the in the constructor, we're going to load this to the stack, which will be put in position 1. The reason that it loads this because we're using a load 0, which will load this, which is in the local variable table at position 0. Then we're going to use invoke special, which we talked about earlier. Please notice in the instruction you've also got invoke special number 1, and you can see on the runtime constant pool we've got a reference to a method which is java/lang/object dot init, and after that we've got something called a descriptor, which we'll cover a bit later. So if you weren't familiar, in any class that you don't implicitly extend anything, the compiler will make it extend an object, and it'll automatically insert a constructor for you, which we'll call the super for the object. That's the code we're currently seeing here. So any constructor for a class that's inserted will be given the method a name init, or which is angle bracket init angle bracket. So whenever you see that, that's a constructor class. The invoke special super is equivalent to having the super semicolon in your constructor. And then we return a void because every method needs to have a void similar to constructor, and the constructor is typeless. Okay, now we're going to walk through the main method, which will print out hello world and show you what it does. Now also notice that in this case we aren't using anything in the local variable table. That's because that we aren't referencing anything that we'll need to use from there. If we were to have a reference to this in it, then that would be in there. Or if we were using the arguments that were run with the thing, then that would also be in the local variable table. But since we use neither, the local variable table is empty. Okay, so first things first, we are going to call getStatic number 2. So if you look in the runtime constant pool, you'll see there's a field value for java/lang/system.out. And after that, you've got a descriptor, again, which we'll cover a bit later. But the system.out is the instance on which we're going to invoke println method on. So that's why we load that. Then we load the constant from position 3, which is the string hello world. So this is the parameter for println, which we'll be calling. And then next, we invoke the method println. As you can see in position 4 in the constant pool, you'll see the method java/i/printstream.println, and that is the method which is being called on the system.out, and the parameter being passed is hello world. And at this stage, you'll see in your prompt or terminal, whatever the command line is, you'll see hello world printed out. And then we return because, again, this is a void method. And that is the end of the program, and that's how the bytecode was carried out. You may have also been wondering when you saw the bytecode before that there was some numbers before each of the instructions. Well, this is simply the bytecode position. So in the hello world constructor, you can see that a load 0 is at byte position 0, then invoke special is at byte position 1. However, the return is not at position 2 as you'd expect, but at position 4. The reason for this is that invoke special is actually taking up 3 spaces. One of those spaces is for the opcode, which the a load 0 also takes up 1 opcode, and return also takes up 1 opcode. However, invoke special has also got 2 extra bytes, which are stored for the parameter index. Even though it's only using one of them because it's only referring one, this allows you to be able to have 65,000 things in the constant pool, around about that. So that's why it'll store every reference to the constant pool in 2 bytes. Okay, so descriptors. Before I said that each as you can see back here, each of the after the invoke special, for example, you'll see the method java/slang/object dot init, and after the semicolon, you've got something that's called a descriptor. So you'll see the parentheses and then v, and you can also see underneath it in the main method, you'll have the field has the method for system.out, and after the colon, you'll have the print stream type. So the descriptor is basically saying what type the field or method is that you're calling. So since you can have multiple methods and fields with the same name in a class, the way that bytecode differs them is by referring to their descriptor. So let's say that you've got a field and it's an integer, then the descriptor for that will simply be I, as seen in the table. If you've got a boolean, then it will be Z. There's different naming because there was conflictions, I'm guessing. So as you can see, boolean and byte would they both can't be B, so they gave boolean C, and character and class can't be C, so they gave class L, and class and long can't be L both, so they gave long J, and then everything else is fine. So yes, if the type is a class, then you need to put the path to it. For example, if the string is, so if, for example, if you've got a type which is a string, we don't have a descriptor for that, so we use L java/lang/string semicolon, and that is the descriptor for a string. If we had an object, it'd be L java/lang/object. If you had a world, for example, that could be L net/minecraft/world/world, which is where the class is for world. And each time you'd have to have a semicolon after that, so it's pretty much L class semicolon. And whenever you see that, that's the type for it. If you've got an array of a certain value, then you'll have to put a left square bracket before it. For example, an array of integers is square bracket I. Any type will just be square bracket type. Now those were for fields as well. So method descriptors have a little bit of an extra thing. So if you've got a method, then you'll need to define the input types and the output type. So if you've got, you'll need to put your arguments, the types of the arguments in the parentheses, and outside of that you put the return type for the method. So for example, if I've got a method which is public string method integer of a string b, so you should know that the parameters that go through this method, or the arguments, are an integer and a string, and the return type is a string. So the descriptor is I ljava/lang/string, and the return type is ljava/lang/string. And you can see that that's the way it's formed out, and that is the method descriptor for that method. If so, you should also notice that there are no separators or anything that separates the different types, so they're all combined up into one thing. That is why the class things have got a semicolon after it to know when it ends. So yes, if we had a descriptor, which is like the one seen in the second last line, you'll see it's an I, L net/minecraft/world/world, and then outside it is a v, then our method may look like a public void method integer of a, int b, int c, world d. So you can see that we've got I, which is for the 3 integers as a parameter, and then a reference to the class world, which is the path to, and it's in the L and semicolon in between it so that we can save that path, and outside is v for void, and that's where the void comes in. Please notice you will actually have to do descriptors and that stuff when dealing with ASM, so make sure you remember this. What is ASM? I've been telling you what bytecode is, but ASM isn't just bytecode. It's the library which enables us to modify the bytecode. ASM comes with your Forge setup, so you can transform classes. Eclipse and IntelliJ have a plugin called ASM Bytecode Outline, which can be used to view the ASMified version of a class. Here I've got the instructions to install it. I recommend you pause the video now and install it for your IDE of choice. As a warning, I'm going to be using IntelliJ, so if you wish to follow along with me exactly, then you can use IntelliJ, but Eclipse users should be able to follow along well as well. So yeah, pause here, and there'll be a link to the Eclipse download because it's not in one of the Eclipse repositories in the description. Another thing you'll need to download is MCP Mapping Viewer, since it is not easy to access the obfuscated names of each of the methods and classes. BSpeakers, also known as Briefcase Speakers, has made a tool called MCP Mapping Viewer, which will allow you to easily see the obfuscated and deobfuscated names of all classes, fields, and methods, as well as their deobfuscated descriptors. So there'll be a link in the description. So the reason this is useful is because when you're in your development environment, you'll be working in a deobfuscated environment, and so you'll be able to use the descriptor for a world as lnet/Minecraft/world/world. However, when you're running it in a obfuscated environment, such as actual Minecraft, and you've shipped the mod out to everyone, it won't be that. It'll be the obfuscated class name, which in this case is actually AHB. So MCP Mapping Viewer will be able to show you the different deobfuscated and obfuscated versions of each of the names, and will allow you to quickly view the descriptor for them to quickly check which one is it. And as a review, you should now know all you need to know about Java bytecode. Now we'll be covering how to create a class transformer in Minecraft using ASM. For this, you'll need to make a core mod. Please note that this core mod does not need to go in a separate folder like it used to. It goes in the mod folder now. For this portion of the tutorial, we'll be using IntelliJ, which is my IDE of choice. However, Eclipse users should be able to follow along. I'm also using Java 7 because parts of ASM don't currently work with Java 8. That is because Forge is currently using the ASM4 API, whereas Java 8 is only compatible with ASM5. This may be fixed in the future, but for now it isn't.